Kelly, this is short and it kind of leads into yours, I hope, a little bit.
All right, we're gonna get started. Then we'll start with Rock. He's gonna give a brief presentation, and then we'll go to Dr. Lepo's presentation.
NASA and the Astro League have an observing challenge right now, and some of you that are really good photographers might be interested, because this is the 35th anniversary of Hubble, and what they've got is they've got some of the objects that Hubble has taken pictures of, and wants you to take a picture during the month that the object is up, and then submit it, and you get a silver award for doing that. And I'll go ahead and go through it.
But we have to come out as good as the Hubble.
No,
Oh,
it doesn't have to be as good as the Hubble.
Because that'd be a bit of a challenge.
You need to do that now.
Oh, yeah.
Hey,
Hacking.
Michael.
It's not going. Hang on. Let me take a look. You lost it. Where'd it go?
No, that's anything except over there.
Okay, well, let's get you to the other screen.
No, yeah.
All right, now try. Hang on. There you go.
So it's hard to believe that the Hubble was launched 35 years ago, April 24th, 1990. And it's forever changed the way we look and understand our universe. And it continues to take pictures that help us understand the universe better. And this award, for the silver award, you're supposed to do an outreach activity during one of the months, maybe get a few other people together and just you have to image or sketch an object that Hubble did, and it have to be done during the specific month for each silver certificate. And all you have to do is 1 month to get the silver certificate. And I'll show you the targets for July. You have to image one or sketch one of them, and identify the parts in the sketch that look like the Hubble. The gold award, you had to start in January, and I tried in January, so I didn't do it. And here's July's. There's a northern list and a southern list. And actually, we can get a few on the southern list from here. Caldwell 69 and 76. 76 is in the lower part of Scorpius, and so you can get pictures of that. And if you want to, but M4, M13, M62, 92, and 107, they're kind of in this like the right ascension that's kind of up right now. So each month is different. Each month has a different list, and these are all objects that were taken by Hubble. And I went out last night, so when I decided to do this, and took a picture of one of my favorites, Messier 4. It's one of the closest globular clusters, only 7,200 light years away. It's pretty bright at 5.63. It's actually larger than the full moon when you get to the outreaches of it. It's kind of a spread out cluster. So there's a Sawyer, I forget the other name, but anyway, there's a way to measure them, and you have to do that when you go through the award. Is kind of guess at what concentration, if it's real concentrated in the center or loose like this one. And this one would be a lot brighter, but it's partially hidden by dark interstellar matter. So it's not as bright as it could be. And here's the one Hubble took. And they zoomed in a lot more. I like going out because I like all those swirls, but they actually discovered a lot of things. They revealed white dwarfs in M4, suspected of being some of the oldest stars in the universe. It's suspected to have had several star-forming events since it was formed. And in 2023, Hubble and the Gaia spacecraft revealed that there's a possible black hole in the center of this one. and here's the two of them together. So anyway, that's gonna be my submission
Yeah,
for
it's
this
the
time.
same.
Huh?
Yeah. He really did.
That looks like a water spring. Water spring with flushing.
But
But-
you're supposed to tell
I
us
don't-
the Hubble one was yours.
Most of them don't have star colors like this one. Most of them are have less different colored stars. But anyway, that's all I have. And now let me give
Okay, hang on a second, let me,
Okay, go ahead.
let me stop your share.
Yeah.
All right, and then we're going to. So Kelly, you should be able to put and share your screen now.
Yep.
Give
Okay.
it a try.
Do that.
There you go.
Okay.
All right, and then Rocky's going to give a brief introduction, and then you're on your own there.
Sounds good.
Dr. Kelly Lepo is an education and outreach scientist at the Space Telescope Science Institute, where she supports outreach efforts for the James Webb Space Telescope. She received a PhD in astronomy and astrophysics from the University of Toronto. During her time in Canada, she made numerous local and national media appearances to talk about everything from the 2012 Mayan apocalypse to the super blue blood moon. She previously served as the coordinator of the McGill Space Institute, taught physics at Gonzaga University, and helped build the Large Hadron Collider at CERN. And her video, see, she got some videos on YouTube, and I'm
Make
really
this
looking
full
forward
screen.
to this.
Hang on. All right, now we're full screen or close to it. All right,
Okay.
Kelly, you have the floor.
Awesome. Thank you. So thank you for that nice introduction. Again, my name is Dr. Kelly Lepo. I am an education and outreach scientist at the Space Telescope Science Institute in Baltimore, Maryland. We're the home of the science operations of the Hubble Space Telescope, the science and mission operations of the James Webb Space Telescope, and also we are home of part of the science operations of the upcoming Nancy Grace Roman Space Telescope. But today I'm going to talk to you a little bit about how astronomers use space telescopes.
Yeah, you're coming in and out, Kelly.
Yeah, I think it might be your end. I'm sort of hearing the same thing.
Yeah.
Turn the video off.
You're
I can
coming
turn the
in
video
fine
off.
for me. Yeah, I'm hearing you perfectly.
Turn the video off where?
Okay, is that better? If I turn my video off? I don't
Yeah.
know.
There you go.
Okay.
I don't know if that's going to affect the audio, but go ahead.
Okay, well, let's see if this works any better. Let me know. Okay, so we're talking about friends in the sky, how astronomers use space telescopes like Hubble and Webb to understand our universe
The audio.
at multiple wavelengths. Okay.
What if she called in on a phone?
I don't know.
We were they read. Guys,
Okay. Well, we'll keep going, I guess. So the inspiration for the title of this talk is this video, which I really love, mostly again for its title. I like to imagine that the Hubble Space Telescope and the Webb Space Telescopes are like BFFs in space.
So Kelly, if I give you my phone number, maybe you can call in and I'll just blast it that way.
Sure, I guess.
All right. So it's 501.
Okay, give me a second.
Hey, Michael, are we going to lose the Zoom presentation if we do that?
I can probably keep the sound on Zoom if they just mute it on their end.
Okay, perfect.
Okay,
Well,
so-
I've muted the sound on my end.
Okay, 501.
And that didn't help.
Okay. What's the rest of your phone number?
You know, whether I'm muted or not doesn't have any effect on you.
Yeah, exactly. So
You
why don't
there?
I call you? And then once the phone call is going, I will you can mute the Zoom audio. I'll keep
Yeah, I did. I
my-
muted the Zoom, but
Yeah. No,
it didn't do anything.
no, I mean, yeah, that's fine. I mean, it probably won't do anything, but what it will do is that the people online will still be able to hear me, and you'll be able to hear me through the phone call.
Okay, that's what I will try to do.
Okay, let's continue. Improvising, this is great. Okay, so Hubble and Webb, friends in the sky. I like to imagine that these two telescopes are BFFs in space. They're long distance friends because Hubble is orbiting around the Earth and Webb is orbiting about 1 million miles away, but they still work together to help us understand the universe. So there are more types of light than what we can just see with our eyes. So we're familiar with visible light, the type of light we can see, but there's lots of other different types of light. Everything from X-rays and gamma rays and ultraviolet light on the shorter wavelength side of things, to infrared, redder than red light, into microwave or submillimeter light, all the way into radio light. So there are, if maybe you could mute your Zoom call. So we can combine all of these different types of light together, and together those are known as the electromagnetic spectrum. So why do we need space telescopes? Well, it turns out that some wavelengths of light are actually blocked by the atmosphere.
I've tried. I've done that.
But we gotta come down to the phone. The clash is.
Guys, I've tried it both ways.
No, but we can't hear.
I understand. We can't hear.
Okay, could you mute your microphone maybe? Okay, there you go. That should be better. So we have the Earth's atmosphere absorbing some wavelengths of light. And I'll turn down my volume here. So there are some, the Earth's atmosphere absorbs some wavelengths of light, including all of the shorter wavelengths of light, like X-rays and gamma rays, and also into the very long wavelengths of radio light. Most of the radio light can get all the way down and into the submillimeter, but also there's another area that's blocked in the infrared. There are some infrared bands that can get all the way down, especially if you're very high up above most of the atmosphere in places that are very dry, because it's actually water vapor in the atmosphere that's blocking a lot of light. But if you want to observe specific wavelengths of light, you have to go to space. And so that is why NASA has a whole fleet of space telescopes, including Hubble, as we were discussing, which was launched in 1990 and is celebrating its 35th anniversary, through Chandra, Swift, Fermi, NuSTAR, Webb, Euclid, Spherex, and upcoming telescopes like Roman and Ultrasat. So why do we observe space in different wavelengths of light? Well, every time you look at different wavelengths of light, you get different information. So for example, here we have some meerkats and a freshwater crocodile. The meerkats have like cute little fuzzy tummies, and we can see this with visible light. We can see the smooth crocodile here. But if we look at this with infrared light, Instead, we see the meerkats, they're actually glowing. And the freshwater crocodile is not glowing as bright because it's about the same temperature as the ground around it. So you and me and this computer I'm using right now, everything that's kind of like human temperature actually glows very brightly in infrared light. And so I'm not lying to you. Here is in fact a selfie taken with an infrared camera of me. And this is the me glowing in infrared light. You can see that my skin is glowing a little bit brighter in the infrared and my clothing is glowing a little bit dimmer in the infrared. And that can tell you about the relative temperature of me and my clothing. So that is one piece of information. There's lots of different types of light out there. Another piece of information that's going to be important for this talk is that things in space come in lots of different colors. So I think if you have spent some time looking at the sky, what you will notice is that stars have different colors. So most people, I guess, if you just ask the average person on the street what color are stars, they'd say white. But in fact, stars come in lots of different colors. So this is a close-up picture, a Hubble picture of the star cluster Omega Centauri. And here we can see all the different colors of stars. So we have bright red stars, we have bright blue stars, we have a whole bunch of sort of yellow white stars in the middle, and smaller red stars. And if you look closely, there's smaller blue stars in here as well. And so the
infrared light, we're not catching
yeah. Okay. I think it's your internet connection there. I don't know. Okay. It'll catch up. So the color of the star tells you about its surface temperature. Very hot objects will actually peak in ultraviolet wavelengths of light. Very cool objects will peak in sort of red infrared wavelengths of light. Maybe if you are still kind of lagging, I'll turn off my camera and maybe that will help a little bit. So that's one piece of information. Stars and other things in space come in different colors. And there's lots of different types of wavelengths of light, including things like ultraviolet and infrared. Okay, so we're going to look at the universe in lots of different wavelengths of light, but first we're going to have to talk a little bit about how we make maps of the sky. So here's the Earth. The Earth is a globe, but we can't actually represent the three-dimensional globe all at once on the screen. So we have to make a map. We have to take this three-dimensional thing and compress it to 2 dimensions. And there's lots of different projections you can use. This is one projection I'm showing here on my screen. It's a Molly-wide projection of the Earth. So we have the spherical globe mapped out into an oval. You can also think of the night sky as a sphere, the celestial sphere. You can imagine the sky as a sphere surrounding the Earth, and all of the stars and galaxies and everything sort of sit on this sphere. There's a couple of points that are important on the sphere. So we'll have the north and south celestial poles, which correspond to the north and south poles of the Earth. And we also have the ecliptic, which is sort of the path that the sun takes in the sky, and it's also the plane of the solar system. So if we take the celestial sphere and we make a map of it, it looks something like this. So you have in this projection, we have a Molly-wide projection of the sky. We have the Milky Way in the center of the projection. And then if we map where the solar system would be in this projection, we have it sort of making an S shape above and below the plane of the Milky Way. The 0, 0 would be the center of the Milky Way. That's where our resident supermassive black hole lives. And if you see anything making this S shape above and below the plane, that is the sign that you're looking at something from the solar system. And if you're looking at something above and below the plane of the galaxy, that's probably outside of the galaxy. And if you're in the center, you're probably in the galaxy. Okay, so that's an orientation about these maps. Now I'm going to show some maps about what the sky looks like in different types of light. We'll start off with gamma rays. Gamma rays, we see sort of the plane of the galaxy showing up in gamma rays, and we see a couple points, like a lot of different points above and below the plane of the galaxy. So what emits gamma ray light? So this is like the most extreme, hottest, most energetic physics happening in the universe. That's things like pulsars, supermassive black holes, supernovas, and these things called gamma ray bursts. So there's two types of gamma ray bursts. One type is two neutron stars, which are the remnant cores of very massive stars merging together. Another is a type of supernova. So those are sort of like the most ridiculously energetic things in the universe will produce gamma rays. Moving down a little bit in to slightly longer wavelengths and slightly lower energies, we have the sky in X-rays. So here again, we see the plane of the Milky Way galaxy. We see a whole bunch of little points, and most of those points are actually not stars, but are in fact supermassive black holes, or at least the disks around those supermassive black holes. And we also see these huge sort of arcing shapes above and below the plane of the galaxy. And those are actually bubbles being blown out by all of the stuff in the center of the Milky Way galaxy, including our black hole. It's sort of blowing out these huge cavities in above and below the galaxy. So what produces X-rays? So neutron stars, the remnant cores of very massive stars, are hot enough that they'll produce X-rays. They're millions of degrees. We have supermassive black holes, or rather the disks surrounding supermassive black holes. The disk that is closest to the black hole will also get to millions of degrees, and that will emit X-ray light. Supernova remnants, this is the supernova remnant Cassiopeia A, that produces X-rays. We have very, very hot shocked gas in there. And things called X-ray binaries, which are either a black hole or a neutron star, like stellar mass black holes or neutron stars that have a normal star companion. And if you pull gas off of this in the disk surrounding the black hole, it will also get very hot, millions of degrees hot enough to produce X-rays. So we can look at this image again and see it labeled. So some things that stand out in this, we see supernova remnants like Cassiopeia A or Vela. We see galaxy clusters. We see galaxy clusters like the Virgo cluster and the Coma cluster. And we see things like we see black holes like Cygnus X1. So Cygnus X1 was the first black hole ever discovered when they set off the first sounding rockets with X-ray telescopes on them in the 1960s. They saw this X-ray point source, and this was the first observational proof that black holes exist. Moving down into longer wavelengths and lower energy, we have the ultraviolet sky. There is no real good map of the whole ultraviolet sky, although that might change soon. So here I'm showing an image. It has lots of black patches on it. Those black patches are where there is no data. But you can kind of make out there's sort of the mid-plane of the galaxy and not a lot else. But what makes up this ultraviolet glow in our galaxy? Well, that ultraviolet glow comes from a couple things, but mostly it's young, hot stars. So we were talking about the different colors of stars earlier, and so the hottest stars, which are have very short lifetimes, will glow very brightly in ultraviolet light. Their sort of peak of emission is in the ultraviolet. The same goes for white dwarf stars, especially very young white dwarfs will glow in ultraviolet light. Galaxies are made up of stars, among other things, and so you will see the young hot stars in galaxies in ultraviolet light, and actually planets in our own solar system. Here I have a picture of Jupiter. And Jupiter has auroras on its poles, and you can see those in ultraviolet light. The visible light sky might be something you're more familiar with. So the visible light sky, here we can see an image from Gaia. And we have the stars in the Milky Way disk glowing in visible light, and then a whole bunch of dots, which are all stars in the halo of our Milky Way. We can see 2 satellite galaxies of our Milky Way in the lower right corner, the large and small Magellanic Clouds. And then we see all of this dark stuff, and that dark stuff is dust. And by dust, I mean like teeny tiny particles of sand and things that resemble soot. The technical term here is polycyclic aromatic hydrocarbons, which I think is a very fun word to say. So visible light, sun-like stars have the peak of their emission in visible light. The same goes for galaxies and supernova remnants. Galaxies are full of stars, and so you will see stars in visible light images of galaxies. Moving on to longer, redder wavelengths, lower energies. Here is a map of the sky in ultraviolet light. Here again, we see the plane of the galaxy, but we see something different in this one. We see that S shape I said to look out for, above and below the plane of the galaxy. And that S shape comes from dust in our own Milky Way galaxy. So we have this sort of warm, we see warm dust from our solar system, sorry. So we are seeing that S shape is warm dust in our solar system that is glowing in infrared light. And then we also see dust in our Milky Way galaxy behind that. That's sort of the orange stuff. Infrared light is produced by the coolest stars. So the smallest, coolest stars will glow most brightly in infrared light. Glowing dust is a big thing. So dust, warm dust, will glow in the infrared. Planets are also about at the right temperature to glow in infrared light. And galaxies are full of dust, among other things, and cool stars. So you will see dust in galaxies glowing in infrared light. Moving on to longer wavelengths, we see the microwave sky. We will see the Milky Way again, the center of the band. We see all of this very cold gas and dust in microwave light above and below the plane of the galaxy. And then if you look in the background, you'll see this glow coming from everywhere in the universe. And that's actually the afterglow of the Big Bang, the cosmic microwave background. So what glows in infrared light? The coldest gas and dust. Things that are a couple of degrees above absolute zero will glow in microwave light. Things like planet-forming disks, the sort of things that are millimeter-sized grains in planet-forming disks will glow in infrared light. Galaxies are full of cold gas and dust, among other things, so you will see galaxies in this microwave or sub-millimeter light. And also, we have this afterglow of the Big Bang, the cosmic microwave background. And then finally, the longest wavelengths of light are radio. The radio sky sort of starts to resemble the gamma ray or X-ray sky. Things that emit radio light are also some of the more energetic processes. So we can see again these sort of curving loops above and below the disk of the Milky Way. Those are the outflows from the center of the Milky Way, and we don't see stars anymore. Stars really don't emit much radio light. What does emit radio light? Pulsars. So these are the remnant cores of massive stars, neutron stars, that have very strong magnetic fields, and through a mechanism we don't quite understand, will emit these like lighthouse beams of radio light, and as the star spins, we will get flashes of radio light pulses like a lighthouse. So we call these pulsars. Supermassive black holes will have very strong magnetic fields. Electrons spiral around those magnetic field lines, and that produces radio light. Same thing goes in supernova remnants. In supernova remnants, you have shocks going out that will excite electrons up to relativistic speeds, and that produces light at every wavelength, basically, including radio light, and also galaxies. So galaxies, you have supermassive black holes at the center. The supermassive black holes send out jets, and those jets can be seen very brightly in radio light. So much so that in this image I'm showing here, the galaxy is just a dot in the center, and we have these huge jets coming out of the galaxy. So we have lots of different space telescopes because each one of those space telescopes will specialize in a different type of light. Hubble, for example, specializes in things from the near UV through visible light all the way into the little bit of the infrared, whereas a telescope like JWST is really a specialist in infrared light. And the Spitzer Space Telescope specialized in even redder wavelengths of infrared light. One interesting thing is that when you're thinking about the sharpness of a telescope, it's like its angular resolution. The size of the mirror really sets this if you are in space. And so there are two things at play here. There's the size of the mirror. So the bigger your mirror is, the sharper your image will be. And there's also the wavelength of light that you're talking about. So the shorter the wavelength of light, the sharper your image will be. So these two things play together. So when we're talking about Hubble and JWST, Hubble at visible wavelengths and JWST at infrared wavelengths actually have the same resolution, about 0.1 arc seconds. It's just that Webb needs a much bigger mirror because it's observing much longer wavelengths of light. Webb is building on this whole legacy of infrared telescopes. There have been lots of different telescopes that observe in the infrared, but what really makes Webb special is this very large mirror to make very sharp images and also to collect a lot of light to see very faint things. And one more piece of information before we move on to the pretty picture section of my talk. We'll talk about spikes. So stars in telescope images, if you have a reflecting telescope, so a telescope that has a mirror, your stars will have spikes. And those are caused by diffraction. So that is light interfering with itself as it interacts with the edges of the mirror and the struts, the supports that hold up the secondary mirror in front of the primary mirror. So I will teach you a superpower. You can always identify a Hubble image versus a Webb image by the shape of their stars. So Hubble has a very standard layout for a telescope. It has 4 struts holding up its secondary mirror, and it has a circular mirror. So the stars will be kind of round with 4 spikes. Whereas Webb has these snowflake-shaped stars, and that's because it has a hexagon-shaped mirror and 3 support structures, 3 struts. So you have the primary mirror is a hexagon shape, and so that will cause 1 spike per star. So that will get you 6 spikes total. And then it also has 3 struts. And so you basically get 1 spike per strut, and that also makes a 6-pointed star shape, but more squished like an X-wing or something. And if you combine those 2 shapes together, you get an 8-pointed star with 3 big spikes and 2 little spikes. And so we can put this knowledge to the test. I will show you a JWST image. So JWST actually also just celebrated its birthday. We celebrated 3 years of science operations. And here, this is the anniversary image from JWST that I'm showing on my screen here. It's of the Cat's Paw Nebula. And actually, it's just of like 1 toe of the cat's paw. And inside of that toe, there's actually lots of little bubbles. And there are these, it's a massive star forming region. And we can see some bright stars in this image. And those bright stars have JWST's characteristic spikes. And if we look at the bottom of the image here, we actually see a bunch of filter names. So that tells you a little bit about how this image is made. So the astrophotographers out there will probably be familiar with this. How we make color images of space is that we take a series of black and white images, we assign them color, and then we stack them together to make these color images. So this is the Cat's Paw Nebula. We'll go to a different star forming area. So right now I'm showing a picture of the Pillars of Creation. So this is a very, very famous area made famous by Hubble, which took its first image of this region in 1995. This is a web version of this image. And what I'm showing here is the different filters that were used to make the image. So how can we make a color image of a type of light our eyes can't see? Well, you just go in chromatic order. So you take the shortest wavelength filter and you assign that blue. You take the longest wavelength filter and you assign that red. And then you pick colors in between and your in between filters, like green or something. And then you combine those all together into a color image. And so the image is a little washed out here. So then you take it into your favorite image editing program. You adjust the brightness and contrast a little bit, and you get your final press released image of the Pillars of Creation. And this is a near infrared view of the pillars from JWST. But you can actually get different information about this region if you look at different wavelengths of light. So in the center of this image I have on my screen here, we see the near infrared view. If we look to the left, we get the visible light view from Hubble. And in this visible light view, we see these pillars are made of very dusty gas. And inside of these pillars, we see baby stars forming, but it's really hard to see exactly what's going on. So then we can go into the near infrared view. Near infrared light sees through most of this dust, so you can really see the dynamical environment and all of these stars forming inside of the pillars. And then if we go to even longer, redder wavelengths of light, what we get is, in fact, the dust itself is glowing. So if you want to see through dust or study dust, we can see that in mid-infrared light. And this is the image I used on my cover slide. This is a multi-wavelength view of this same area where we have stacked all of these images together. So this combines data from Hubble in visible light, Webb in near and mid-infrared light, and also data from Chandra in X-ray light. And so what we see here is that the purple is X-rays, and we see some of the stars actually have purple dots around them, which means that they are in fact emitting X-ray light. So it turns out that actually young stars are pretty good at emitting X-ray light because they have lots of flares. So think of like flares from the sun, but times that by like 100 when you have very young stars. And so you can see X-ray light from some of the stars forming inside of this star forming area. So pillars form because stars like to blow bubbles around them. So we have these little pockets of gas where stars have formed, these very hot young stars. They'll blow bubbles around them. And then inside of these bubbles, you'll have little bits of gas that are denser than the rest. And those will shade the area behind them. And you will get pillars that look like this. And so the stars are always above the pillars, and the area on the bottom of the pillars are what's being shaded. And that is why we get these pillar-like structures in lots of star-forming regions. I do have a video, but I'm going to skip it because I don't think it's going to work with the slow internet connection. Okay, so another star-forming region. So this is a Bok globule near the Gum Nebula. So it's a little globule, a little bit of gas and dust. It's very dusty, very cold, molecular hydrogen gas cloud. And we see a little jet coming off of this globule, but we can't really see what's going on inside. And that's because all of the dust and this gas is blocking our view. So we see stars strewn throughout this image, but not in the upper left portion where this dust is. If you actually look at the edges, you can kind of see like orangey stuff, and that's because the dust is absorbing most of the blue light, but letting the red light through. So this is a problem if we want to know what's going on inside. So let's look in with JWST and infrared light. The infrared view is much different. We can see the red spikes at the center of this image. Those red spikes are actually binary stars that are forming. And these stars are messy eaters, and the stars are shooting out jets. And those jets are ramming into the gas around them and carving out these very long oval shaped cavities. And we can see the edges of these cavities glowing in infrared light. And basically that dark nebula disappears, or you can see it a little bit, but not that much in infrared light. And then we can get the same slightly longer wavelength view with Spitzer. We again can see the edges of the cavity and some of the background stars, not so much the nebula. And then if we go to very long wavelengths, we get the radio or like sub-millimeter light view of the pair of forming stars. And what we can see here is the cavities. And here this is color coded. So blue is moving towards us and red is moving away from us. So we get like a 3D view of what's going on. The jet that was poking out the nebula is pointed towards us, and the jet that was embedded in the nebula is pointing away from us. Okay. Another multi-wavelength view of space. This is the Rosette Nebula. It's a favorite target of amateur astronomers. And here we have an infrared view of the nebula. We see two types of dust in this view. We have in the center, the red area is like this sand-like carbon dust. And then on the outer bits, the green bits, we have this soot-like hydrocarbon dust. So we have these two different types of dust glowing in this nebula. But if we look in visible light, we have a little bit of a better view of what's going on. So what has happened here is we have a cluster of stars that has formed in the center of this nebula. These stars are very hot, they're very blue, they're emitting lots of ultraviolet light, and also they're blowing winds, and they have carved out this bubble around them inside of this nebula. And in visible light, we are seeing different elements glowing in different colors here. So the yellow is oxygen and the red is hydrogen. And if we look at the top, we can see a little sort of wrench-shaped object here, and that's a pillar. And we can see all of these pillars again are pointing towards the center of the nebula. And these pillars are very dusty, so they appear dark in visible light, whereas they were glowing in infrared light. And we can actually zoom in to a portion of the Rosette Nebula, talking about Hubble's 35th. So this is one of Hubble's anniversary images. It's just a small, tiny section of the Rosette Nebula. And here we see the dust in these pillars, which appears very dark because it's absorbing a lot of the visible light. And at the tip of what we were calling the predator or the alien here, it has sort of a glowing eye. That is a forming star that's embedded at the end of this little dusty area, and it's shocking the gas around it, heating it up, and causing it to glow. If we look at the same area in ultraviolet light, so shorter wavelengths, the nebula almost, but not completely disappears. And what really is highlighted are the stars. So we can see the hot young stars in this star cluster in ultraviolet light from galaxies. And if we go to even shorter wavelengths, if we look at this in X-ray light from Chandra, and so I don't actually have a full view of the Rosette Nebula in X-rays. We only have a portion of it because the Rosette Nebula is actually pretty big on the sky. But we have several pointings from Chandra of this area, and we see all of these little dots. And almost all of these dots are in fact young stars still embedded in their cocoons of gas and dust that again have very strong magnetic fields. They're shooting off flares and they're glowing in X-ray light. So it turns out that X-ray telescopes are actually really good at finding embedded protostars, which is not something that I would have thought. But when I was working on a project on the Rosette Nebula, I found that out, which I thought was cool. Okay, so we were sort of talking about star forming regions, which you can learn about star forming regions near to us inside of the Milky Way. So we're going to take a slightly wider view now and talk about what we can learn about galaxies as we look at different types of light. So here is M74, the Phantom Galaxy, in a visible light view from Hubble. So remember how we said that the hottest, youngest stars glow very blue. So blue stars have very short lifetimes, which tells you if you see a concentration of blue stars, those stars have to be fairly young. So if we look at the outskirts of the galaxy, we see all of these blue stars, which tells us that there are recent sites of star formation. As we go to the center, the galaxy appears to be more yellow. So as the stellar populations age, so as more time goes on, all of those blue stars will have all died off, exploded as supernovas, and all you are left with are the cooler stars. And so those stars will appear yellow. So generally, when you look at spiral galaxies, the center will be more yellow. That's where all the older stars are. And the outskirts will be more blue. That's where all the younger stars are. We also see dust filaments winding their way through in these spiral arms. They help define the spiral arms. And we see also like red areas. And those red areas are areas where the galaxy is currently forming stars, and the star formation is heating up the hydrogen gas in that area, and it is glowing red. So that's what we can see in visible light. As we move to redder wavelengths, we see different things. So now I'm showing a mid-infrared view of the same galaxy, M74, and it looks a lot different. And that's because almost all of the stars have dropped out. When we're talking about mid-infrared light, very few stars are cool enough to produce mid-infrared light. So what we're mostly seeing here is actually glowing dust. So all of that white stuff is actually dust, and we see lots of bubbles in this dust, and that's where stars have formed. They've blown out the surrounding gas and dust, and then some of them have exploded as supernovas, which creates even larger bubbles, and then some of those bubbles merge together and they make super bubbles. And so when you look at mid-infrared light, galaxies look very bubbly in a way that I kind of find slightly disturbing, actually. And in the center of those galaxies, what you will see is the oldest, coolest stars. And those are at like the bluest wavelengths of mid-infrared light. So the shortest mid-infrared wavelengths, you see a couple stars. So the center of the galaxy looks blue. In ultraviolet light, however, you will just see the young stars. So here we have a ultraviolet light image of the galaxy, and we see young star clusters. And then if we look at the same galaxy in X-ray light, we just kind of lose the galaxy entirely. In the center, we see a point, and that is from M74's supermassive black hole. Supermassive black holes have disks around them. The disk closest to the black hole will reach millions of degrees, which is hot enough to glow in X-ray light. But basically, all of the other points are either background supermassive black holes from other galaxies, or they're X-ray binaries in M74. So those are neutron stars or black holes that are pulling gas in from a companion. And they're sort of randomly scattered throughout. So you kind of lose the galaxy entirely. Okay. So that was what we can learn about sort of within our Milky Way at different types of light, what we can learn about galaxies. But what if we want like a really big picture? So we're talking about Hubble's 35th birthday. One of the most consequential things that Hubble did was in 1995, some scientists went to the director of the Space Telescope Science Institute and they said, what we would like to do is we would like to point the telescope at an otherwise dark patch of sky for 10 days. And this was very controversial. Some people said we're not going to see anything. Other people were like, yeah, let's do it. Let's do some science. Let's figure out what we see. And so they saw something that looked a whole lot like this. So this is the follow-up, the Hubble Ultra Deep Field from 2014, but it looked very much like this. And so this image has 10,000 galaxies in it. Almost every single point of light in this image is in fact a galaxy. There are a couple stars, the stars have spikes on them, but almost every other point of light is a galaxy. And so with deep fields like this, we can understand the history of the universe by picking out individual galaxies at different times in the history of the universe and studying like what the average galaxy was like at that time period, comparing galaxies very close to us to galaxies that are very distant. So how do we do that? Well, we use the fact that the universe is expanding. So galaxies emit most of their light, let's say at ultraviolet or visible wavelengths of light, where stars emit most of their light. But as light from very distant galaxies travels to us through the universe expands, and that will redshift that light all the way from, for the most distant galaxies, from ultraviolet and visible wavelengths into the infrared. So that means that as we look for more distant galaxies, the galaxy's light has taken longer to reach us, and the more red-shifted its light will be. So if you want to see some of the first galaxies to form after the Big Bang, we can't use Hubble, because Hubble can't see that far into the near infrared, and also it doesn't have a very large mirror. Instead, we need something like JWST, which has a very large mirror and can see all the way to the mid-infrared. And that gives us a view into some of the first galaxies to form after the Big Bang. And we can only do this with infrared telescopes. And you also, if you want to see these galaxies, they're very, very faint. So you also need a telescope with a very large mirror. And JWST has that as well. So we can make deep fields with JWST looking for these first galaxies, just staring at patches of the sky and trying to collect light from galaxies throughout the history of the universe, but we're especially interested in what some of these first galaxies would be like. So here is Hubble's record holder. It's a galaxy called GN-Z11, and it's a little bit of a weirdo, which you would imagine because it's the furthest galaxy that Hubble has ever seen. So that's Hubble. Here is the same galaxy with JWST. It looks like a dot, but it has a dot with a little bit of fuzz. So we're actually resolving a little bit of the structure of this galaxy. And we can see it in a whole bunch of different filters. And we can learn about this galaxy in a way that we could not with Hubble. We were really pushing Hubble to its absolute limit, but we have so much more information with JWST. For example, here I'm showing a spectrum of this galaxy. So I'm taking the light from the galaxy, I'm spreading it out like a rainbow, and I want to figure out what this galaxy is made out of, basically. So if we look at the Hubble spectrum on the left, it kind of just looks like noise. Like if you squint, it kind of looks like something. You can convince yourself it's a galaxy. But the JWST spectrum is just so much better. We can see the very characteristic curve that a galaxy would have. It cuts off at the Lyman alpha line. We can use that to find its redshift, but also we see peaks, and those peaks correspond to different elements. So we can see that there's carbon and magnesium and oxygen and hydrogen in this galaxy at a redshift of 10.6, which is about 400 million years after the Big Bang. So this works, and it always really surprises me that it does. The current record holder asterisk right now is this galaxy called Jade's GS-Z14. And this is at a redshift of 14.32. But there's actually another galaxy that is slightly further away, and that galaxy is going through peer review right now. So this one is the record holder for now, but that will change soon. We're seeing this galaxy as it was about 300 million years after the Big Bang. And so with this like new window into the universe, because we are looking at infrared light in a way that we couldn't with Hubble, we're learning things about what the early universe was like. So we are discovering very bright galaxies there, which means that these galaxies must have formed a bunch of stars already. We are seeing galaxies that have black holes that are sort of larger than we would predict. Maybe that's actually true, or maybe we're just measuring the mass of those black holes wrong. We are seeing galaxies in this first 300 million years which have already formed a bunch of stars and then shut off star formation. We are seeing, if you look in the first billion years of the universe, we are seeing spiral galaxies already appear. There was this idea that spiral galaxies were sort of a recent phenomenon, but it seems that spiral arms are really easy to make. So even in the first billion years, we're seeing signs of spirals because now we have the spatial resolution to pick them out. We are seeing an analog of the Milky Way, like 600 million years after the Big Bang. So like the big idea here is that the galaxies evolved faster in this couple 100 million years after the Big Bang than we were predicting. Not like break the Big Bang theory bad. It's just like, you know, it's slightly different in detail than we were imagining, which is always kind of interesting. That's like a really fun place to be as an astronomer. Another interesting thing that popped up, so the image here isn't that interesting, but I swear that it actually is really cool. When astronomers were looking through their deep fields, they kept finding these very, very concentrated, very, very red objects, and they called them little red dots. And it turns out that a lot of these objects are appear about 600 million years after the Big Bang, and then they're almost all gone by about 1.5 billion years after the Big Bang. So it seems like there was something that only existed in this early period of the universe. And it seems like from a couple different pieces of evidence, what these are actually supermassive black holes that are shrouded in a lot of gas. So normally in the local universe, you could have shrouded black holes, but they'll be shrouded in both gas and dust. And these seem to be just gas. So early in the history of the universe, there wasn't a lot of things other than hydrogen and helium. This was like pristine gas after the Big Bang, and it seems to be feeding and surrounding these black holes and making these little red dots, which is cool. This was something that was completely unexpected, but found when looking through JWST data. And if you want to learn more, we actually did a recent public lecture on the Space Telescope Science Institute YouTube channel. So you can check that out and hear from a scientist about all about little red dots. And so that is all I wanted to talk about today. We went from nearby star forming regions all the way to the end of the universe, talking about why it is interesting to observe things with different types of light. And so I will leave you here with the center of the Milky Way in different wavelengths of light, from Spitzer infrared, Hubble near infrared, and Chandra X-ray. If you are curious, the center of the galaxy and our resident supermassive black hole, Sagittarius A star, is in that little white spiral-shaped structure to the right. And you also see these big arcs, which are magnetic fields. They're just crazy strong magnetic fields at the center of the galaxy. And it's kind of like if you've ever played around with a magnet and iron filings, it makes these sort of arc shapes. And you can see that in the gas that is in the center of the Milky Way. It's really cool and weird. So yeah, that is the image I will leave you with. And I'm happy to answer any questions if there are some.
Any questions here at the library? No? No? All right, well, thank you very much for your presentation. Sorry for
The technical difficulty. Yeah, that's okay. We made it through, hopefully.
Now we're gonna have to talk to the library here. Hopefully they'll speed up their thing, or next time I can get a hotspot going.
Okay. Do we see a question? I think I see a question.
I have a question. Can you describe how the James Webb Space Telescope is able to determine atmospheric composition of exoplanets? I've seen some of that.
Okay, so the question was how can JWST determine the atmospheric composition of exoplanets? So you have a planet and it'll go in front of its star. And some of that starlight will filter through the atmosphere. And the atoms and molecules inside of the atmosphere of that planet will absorb very specific wavelengths of light. So things like water or carbon monoxide or carbon dioxide, those molecules will absorb very specific wavelengths of light. So what you do is you take a spectrum of the star as the planet is going in front of it, and then you subtract the star's spectrum and you get just a spectrum of a planet. And you compare that to models that you make in advance of what planet atmospheres could look like. And you use that to determine the composition of planets, the atmospheres of planets. And that also is one of those things which like blows my mind that it works. Like there's a planet that's 1,000 light years away and we know what its atmosphere is made out of. Like, I think that's cool.
Yeah, that's amazing. You know, you think about the scale involved in being able to determine what its atmosphere is probably. So has there been any likely exoplanets discovered that have atmospheres similar to Earth?
Has there been any similar to Earth? So not so far. So what we're really limited to right now are mostly things like hot Jupiters. So that's something like the size of Jupiter, but within the orbit of Mercury. So that is very unlike the Earth. It's very unlike anything in our solar system. Or we've actually observed a couple rocky planets orbiting around their star. And that is so hard to do that we're not really measuring composition there. We're mostly like a binary, like does it have an atmosphere? Doesn't it have an atmosphere? So if it has an atmosphere, it will tend to redistribute the heat of the planet a little bit from like the night side to the day side, and that changes the temperature of the planet. So you can measure the temperature of the day side of the planet and compare that to models and say like, oh, this probably has an atmosphere. Or, oh, this is probably a bare rock. And even those planets are kind of not like the Earth. They're usually a lot closer. They're again like within the orbit of Mercury. You want something that is orbiting pretty closely. So not yet. What will probably, if you want to measure the atmosphere of an Earth-like planet around a sun-like star, you're going to need something like the Habitable Worlds Observatory, which is coming no sooner than the 2040s. So that right now we're sort of developing the technology that we need to make a measurement like that.
No one else has any. Looks like most of the planets.
Thank you very
Okay,
much. Appreciate it.
Thank you so much.
thank you.
All right, well, I'm gonna end the meeting and everyone take care. Have a good safe night.